I was hogging the microphone. Hear me okay?
Yeah.
Coming across? All right.
Yeah.
Is that a little better? Okay. Yeah, my name's Berdie. It's always a pleasure to come out to YAAS. I do have some family down here. She may deduce from the name on the board, but always a great opportunity or excuse to come down, so thank you for having me. As Adam mentioned, I'm a remote sensing professional. I've been doing this for about 18 years at this point. Started out doing wildlife research, and a lot of what you're doing with that line of work is looking for assessing habitat or habitat suitability of animals, and through that I was exposed to some of these mapping technologies as an alternative way, instead of tromping around in the forest directly, as a way to assess habitat and changes to habitat over time. So at some point got tired of falling down mountainsides and shivering in the rain, and decided to go back to school. Got my graduate degree in geography and in remote sensing, and have been working in the field ever since. So I'll get into a little bit of what remote sensing is here shortly. And just kind of for the structure of the presentation today, I'm an applied scientist, not a research scientist, and the way I think of that is work for commercial firms that we tend to take understood principles, scientific principles, these technologies that may have been invented or discovered often in academia or in pure research settings, and apply them to real world applications. And so to me, that's really the fun and exciting part, is affecting change in the world through the use of these technologies. So I will give kind of some background and overview of some of the science. At this point, I am more of a manager of scientists, so we'll keep it at a high level, because I can't go as deep as I used to be able to, and hopefully that keeps it a little more accessible as well. And then we'll spend some time of a lot of use cases, and I'll just kind of cruise through those, and I'll try to leave some time at the end for questions if anything sparks some interest that we want to talk a little bit more about. So just as an intro, kind of some vocabulary that I'll be throwing around out here. Remote sensing I think of as kind of the science of these various technologies. Typically camera technologies that we are using to map and monitor the Earth. And that's how I think of as remote sensing, and that's typically a term that you hear in academia. In the commercial world, we tend to use this term geospatial, which I think of as kind of the aggregate of remote sensing professionals, camera manufacturers, software providers, everything that goes into creating an industry that leverages these technologies to solve business problems or real world problems. And why do we use remote sensing? Some of the key benefits of really what we're doing is monitoring the Earth indirectly or from afar. And so instead of having to be on the ground taking measurements directly, we're able to leverage these technologies to map and monitor the Earth. And a couple of the advantages, one is really scale. To be able to leverage some of these platforms, if we're using satellites from space or aircraft that we're flying, we're really able to look at these areas that we're studying at a global scale or a continental scale. If you want to understand how the forests in the Amazon are changing, that's a tough ask to do that through direct measurement on the field. There's certainly a component of that supports the indirect measurements, but to be able to do this at large scales, or this type of work at large scale, is really one of the advantages of these technologies. And then the other thing is that idea that we are doing these things indirectly means that we have an opportunity to potentially have less effect on the subjects that we're studying. As a wildlife biologist, we might go in sometimes and trap an animal to collect some sort of data or track it over time. But in doing so, you're always kind of have the concern that you may be affecting the outcome of the study that you're conducting by your presence. The fact that you've trapped this animal, are you changing its behavior? And so remote sensing, these technologies allow us to do some of these types of studies indirectly without removing that risk of affecting the subjects that we're studying. So remote sensing, geospatial, is kind of this aggregate of sensors. Think of fancy cameras, and I'll dive into what some of those look like, and platforms, things that we're attaching our cameras to. And some kind of general families, satellites, we've really seen over the last 5 years especially, but over the last decade, really the commercialization of space to the point that somewhere around 3,000 satellites were launched last year. It's around 7 or 8 a day. Basically none of those from NASA. That's almost, obviously that's globally, so lots of other government agencies are putting satellites up, but a lot of that is from groups like Blue Origin and SpaceX. So really this kind of commercialization, and satellites that we're talking about are often this kind of breadbox size, small sat systems that are going up these days. So commercial entities will do things like launch flocks of satellites. They might send up 40 satellites as one kind of mesh system. Groups like Planet Labs is a well-known satellite image provider, and they have enough satellites up in space that they image the entire Earth every single day. So lots of satellites going up become, some of the advantages of that are, again, scale, the ability to image large areas. To acquire satellite imagery tends to be very inexpensive, a couple $100 to buy a satellite scene. You can task many satellites. You can say, dictate, I want an image over this particular location. That's where you start to pay some more money. Some of the drawbacks of satellite platforms are you often are looking through cloud cover or smoke, and so times where you might really want some of this imagery, during a hurricane, maybe during wildfire season, you have smoke and clouds that are potentially getting in the way of your imagery. So some drawback to satellite imagery, and the quality of the imagery, the resolution or the objects that you can see tend to be not as good as some of the other platforms. Sort of a Goldilocks option in between is airborne platforms, so acquiring imagery and data from helicopters or aircraft. Advantages tend to be a lot of control over the payload. You can swap out different types of sensors depending on the mission that you're trying to achieve. Very high quality data at still large scales. So if you want to acquire data over the state of Oregon or the coast of Oregon, these type of airborne platforms are a good candidate. High resolution, high quality data at not global, not continental scales, but still potentially large scales. Cost tends to be a little bit higher. Might be looking at $1,500 an hour for an aircraft with crew and sensors loaded, so can be quite expensive, and that's probably the major drawback of a system like that. And then ground-based system. These might be mounted on vehicles. We see as part of not just collecting data for the autonomous vehicle industry, but many of our new vehicles today have either LiDAR or camera systems on them to support assisted driving. Those types of systems, so maybe on a vehicle, maybe on a tripod, if you want to monitor a specific location over time. So these ground-based systems, least scalable. If you're on a car, you can only collect data where there are roads. And if you're on a tripod, obviously picking that up and moving it, you're limited to kind of where you can get on foot. But very high quality data. If you want to map something in a very small feature that exists in the world, these are, it's a good platform to mount your system onto. So some types of platforms that you might mount cameras to. And then just kind of a couple families of sensing instruments that exist, and I'll get into some specifics, but we think of active systems, and these are systems that bring their own energy, their own energy to support the detecting of whatever it is you're monitoring. So systems like LiDAR or radar, where you are emitting a pulse of energy, and then the system is making a recording the impact of that. And those systems, that power can be a constraint. There's also some constraints around some of those active systems don't work as well from space. Shooting a laser from space is a big laser, some safety issues, and just the power required becomes a challenge. The other types of systems are passive systems where they're not emitting their own energy, they're using energy from the earth, whether that's heat or sun rays, sunlight, things like that, and I'll get into some more details there. But all we're doing is we are looking at a specific problem that we want to solve by leveraging these technologies is we're mixing and matching. We're saying, what's the right technology that's going to answer the question we're trying to answer, and how do we deploy that technology best? What platform do we want to put that on? the life cycle of a project, a research project, or an applied project is you're acquiring data, you're processing that data, and you're analyzing and ingesting or consuming that data. So the data acquisition I kind of spoke about, but lots of kind of logistical aspects to think through that aren't necessarily apparent on their surface. Deploying a satellite, you may well have to wait for SpaceX to be available, and that schedule can be irregular to get your satellite into space. If you have a satellite and you want to acquire imagery, even our national security agencies these days leverage primarily commercial satellites. And so if you as a scientist want satellite imagery over a specific area, you are almost always going to be behind, in the back of the line, behind national security, who may want that satellite to be tasked over an area of interest, based on current events or whatever. So, everything from restricted airspace. We did a project that was adjacent Disney World. It was the most difficult project we had to acquire data, because Disney controls the airspace very tightly around its theme parks. So it was challenged to find times that we could fly our aircraft adjacent to Disney theme parks. But you collect your data, there's a fair bit of processing that occurs. You are calibrating the data, making it accurate. These are things that we want to be able to take measurements from and analyze these data. And so there's a lot of work to make the data analysis ready. There's a lot of artifacts that may exist in the world. Again, we're acquiring data in the real world. It's not in a lab. This is not in a clean room. And so anything from birds in the data to smoke in the air, all of these things may affect our instrumentation. And so you have to normalize your data to clear that out so that we know that the measurements that we're recording from the data are accurate. And then you're doing some sort of analysis, and obviously through the use cases, I'll kind of give some examples of what that looks like. But then you're analyzing these data, and techniques today, AI and machine learning, not as much generative AI in here, because we're trying to look at what exists on the Earth, not something we're trying to manifest in a generative way, but different types of machine learning models we've been using in geospatial for 15 years in a very applied way. And so it's great to see kind of the continued advancement of those technologies, much more accessible, and the infrastructure that supports machine learning has really grown over the last few years, making it much easier to access those types of approaches to analyzing large data sets. And these are large data sets. The firm I recently worked for, we acquired over 60 petabytes of data last year. So the IT infrastructure, the compute infrastructure that's required to ingest, to store, to analyze these data sets is massive. And of course, cloud compute has really, again, made a lot of that much more accessible. And then GIS is maybe the term that most people have heard in this world. Can I show of hands? Can I see who's heard of GIS? Okay, so at this point, yeah, if you have Google Maps on your phone, that's a GIS system. And so a lot of what we're doing in remote sensing is we're creating data that we then may deliver or serve through a GIS system. So there's all this information in detail that we may be acquiring. We're going to distill it down to simple lines and polygons that we can put on a map. And that's how we can much more easily interact with the output of some of these data sets. Just a couple more basic principles before I get into some use cases. You'll hear me use the term resolution, and in the spatial resolution that we kind of illustrating on the screen is kind of I think the easiest to grasp. But really, we're talking about imagery, or we're talking about pixel size. And again, satellite imagery, you might have a coarser pixel size. Here in the lower left, we have a 10-meter pixel. So each square in that image is 10 meters across. 1 meter image and 30-centimeter image. 30 centimeters is about the highest resolution satellite imagery that's available today, about a foot. There are tricks that you'll see groups say there's 15-centimeter, 10-centimeter imagery out there, which is true, but there's kind of some machine learning tricks that they use to take 30 centimeters and make it look like 10 centimeters. But regardless, typically there's this trade-off between coarse resolution, inexpensive, not as much issue to store those data, smaller data sets, but the types of things that you can map are relegated to larger areas. But if you're trying to map how much forest cover we have in Oregon, a 10-meter scale is probably just fine. If you want to map the pipes in that scene, you need a much higher resolution image. The trade-off there again, higher cost, and the compute storage that you need to work with those data sets is quite a bit higher. But the fundamental principle here is something called the minimum mapping unit. You can't map anything smaller than your resolution. So you cannot map a pipe that is 6 inches across if you only have, or 1 foot across if you only have 10-meter imagery. So you always have to try to fit your data to the mission. Last kind of concept is accuracy. We spend a lot of time thinking about and working with our data to make it accurate. And there's kind of, I'll stick mostly with the spatial accuracy, but a lot of the data that we're acquiring, we're working with, again, we want to make sure that our measurements are accurate, that we're taking from that data. And so there is often a meaningful ground truthing component where we are collecting data directly on the ground and then comparing that to the data that we acquire remotely and making sure that we have alignment or agreement. And you kind of see there the bullet points, some examples of different types of data and the accuracies that can be achieved. With imagery, like we see here, 2 to 3 pixels is about what we're able to claim from an accuracy standpoint. So if that pixel is a 1 foot pixel, the accuracy of your data can be 2 to 3 feet, which means if I say this stop sign exists at XY location, I'm plus or minus 2-3 feet off. Good for a lot of purposes, good for mapping purposes, maybe not good enough for, say, engineering or design off a data set like that. For those types of applications, you might use a technology like LiDAR, where you can get 6-10 centimeter accuracy pretty easily from an aircraft, 3 centimeter or 1 centimeter accuracy from a tripod. These data sets for most firms are going to be signed off on by a professional land surveyor. So they are survey grade data, which means we can fly an airplane and map an area, and you can design off of that, and it will be legal tender, the same as if you had a surveyor come out with the yellow total tripods where you see people shooting directional measurements there. And then some technologies, like synthetic aperture radar, is actually sub-millimeter accuracies. So with that type of application, you're able to do things like look at movement over time of the Earth. Things like fault slide or landslides or fault lines, subsidence here on the West Coast, obviously, something we're very interested in. So monitoring those type of millimeter scale changes of the Earth, you would use a technology like synthetic aperture radar. I'm going to get into spectral properties here in a second, so I'll hold off and maybe just talk through that on another slide. So I'll get into kind of highlighting one of 2 technologies I'll kind of spend some time on today, but it's a large family, and this is spectral imaging. This is a near IR, an infrared image of YAAS. This was taken in 1993, I think probably just with a film camera that had infrared imaging, and what infrared imaging is used for is to map vegetation. Vegetation reflects very strongly in infrared wavelengths. And so it's very easy to understand and map vegetation with this type of camera. But just to step back for a second, spectral imaging, the science of spectral imaging, is a passive technology. We're taking advantage of the energy emitted from the sun. My jacket looks blue because it is emitting blue light back to your eyes. It is also emitting near infrared and ultraviolet, all sorts of other wavelengths of energy that our eyes can't see. Remote sensing is using cameras that can see those other wavelengths of light to see things on Earth that our eyes might not be able to see. We see from, I want to say, 400 to 700 nanometers, red, green, and blue. That's what our eyes see. But again, these cameras see different wavelengths of light, and we can take advantage of that. Just kind of to drive that point home, other animals can see different wavelengths of light. In the upper right is a damselfish, and it's being imaged with an ultraviolet sensor. So we see that fish on the left in red, green, and blue, and so all we see is this yellow wavelength of light. It is also emitting in the ultraviolet wavelength this completely different pattern that our eyes can't see, but an ultraviolet camera can. And guess what? Damselfish see in ultraviolet. So these fish look very different to each other than they look to us. Just another example here with the European starling in ultraviolet. Again, many birds can see in the ultraviolet wavelength. You can do the same thing with flowers. So how do birds differentiate between different flowers, or hummingbird differentiate between different flowers that it might be interested in feeding on? They are looking at these things that may, in many cases, see patterns that are not visible to us, but visible through these other wavelengths of light. So first application, I mentioned vegetation. The near-infrared band has been something that's been being used for a long time. Landsat satellites have a long legacy in remote sensing sciences. I think we're on the 8th Landsat satellite that's been up and maintained by NASA, going back around 30 years. So in terms of having a legacy to be able to look back over time, you'll see Landsat imagery is one that researchers take advantage of. It's not very high resolution anymore. It's about compared to what's available today. It's a 30-meter pixel. So we're looking at pretty large tracts of land, 100 feet across or so, that we can make any assessments about. But this was a study that was done here in Oregon, specifically in our coastal communities, and they used what's called NDVI, and you can see the equation there, but it's basically a ratio between how much of this infrared light is absorbed and how much is reflected. Again, plants, chlorophyll reflects very highly in that near-infrared wavelength. And so by looking at how much of that near-infrared light is absorbed by non-vegetation and reflected by vegetation, we can map vegetation with great accuracy. You do that over time, and you start to get a sense of how your forests are changing over the years. Lots of other studies comparing those changes to different land management practices, et just try to understand causational relationships between land management and forest cover. But what this study found is that looked at 80 of Oregon's coastal watersheds, and they found serious logging had occurred within those sensitive habitats, those community watershed areas. And so as part of that, that data supported some legislative action where this Community Drinking Water and Protection Fund was created and funded by the state of Oregon to try to help support some of the activities that were occurring in this. But land cover change, vegetation to forest mapping, long legacy of that type of work with remote sensing. That was really focused on this kind of red, green, and blue color scheme, a little near infrared. Imagine that's kind of the color crayon box. Maybe you got 8 crayons in there. You can paint a nice picture with that. This technology called hyperspectral imaging. Now we're working with the jumbo box of crayons, all the colors, 10 different variations of green. And really, some of these cameras might have 360 different wavelengths of light or 360 different color channels that they can analyze the world in. And this is used for much more sophisticated vegetation mapping is one use case here. We see on this graph along the x-axis is the wavelength of light, and on the y-axis is how much energy is being reflected. So can anybody guess? We have one little peak here. We have a lot of energy being reflected right around this 580 nanometers. Anyone want to guess what color 580 nanometers is? It's green. Trees look green because they're reflecting green light. But you see there's not much differentiation between those bands. Whatever light purple is, box elder, maybe a little deeper green or something. But it's difficult to tell the species of tree just from looking at the green color. But if you're able to look out here into the ultraviolet wavelengths, suddenly you see that these different species reflect this wavelength of energy very differently. And so we can acquire this type of data over huge forests, train a machine learning model to differentiate between this, what's called a spectral signature, differentiate these spectral signatures, and map the species of every tree for an entire forest. I'm saying that like it's easy, it's not really. You have multiple trees, showing up in a single pixel. So it gets complicated quickly. That's where we go back to how accurate are we with some of these mapping, but very cool technology, huge data sets, massive compute and storage required to work with these types of data, because there's so much information being collected, but very cool application. And I'll give you one example. Someone hired the firm I worked for. They managed, it was Duke Energy, and they managed large electric utility across 5 different states. And in the Midwest, they had emerald ash borer as a pest. And it's a beetle, and it was killing all ash trees. And it was only a matter of time. It was well agreed upon by the DNR in that area that all ash trees in that region were going to die. And a dead tree adjacent to the power line is a very real fire risk if a dead tree falls into that line. And so Duke Energy hired my firm to fly a helicopter over thousands of miles of power line and find every ash tree adjacent to their power lines, and then they mitigated that risk. So it's an applied example of why you might want to find a particular species out there in the world. This was a cool project I was a part of, 10 years ago or so when I worked on this project, and this field has advanced quite a bit. I worked with a large agro-technology firm out of Germany, and we're using that same principle where different species may reflect different amounts of energy. A single species may reflect different amounts of energy across different wavelengths depending on the condition of that plant. So if the plant is photosynthesizing effectively, it will reflect a certain way. If it is not photosynthesizing efficiently, it will reflect a certain way. If there is a fungus that may be growing on the crop, that will show up in that spectral signature. And so what this firm, what their business model was that they're trying out, and this has been realized by several companies since then, is me as a farmer, and this is a center pivot crop field. Traditionally, I might spray fertilizer, nitrogen across my entire field. I might spray pesticide across my entire field. What this model was I would pay a subscription fee, and once every 2 weeks, someone would come and fly a drone and collect this type of imagery over my field. That would then be processed and analyzed to look at nitrogen needs, fertilizer needs, water needs, look for some basic weeds and other pests that may be present in that area. And then in the mail would come to me my chemicals and the little GPS card that I would plug into my center pivot. And that center pivot would go around my field, nitrogen, water, pesticide. So really reduce the chemical load required to maintain these fields. So kind of a win-win. The company that gets paid to sell chemicals reduces their costs because they don't have to make as many chemicals. Great for the land and the farmer because they don't have to apply as many chemicals to their fields. And happy for us who are not eating as many chemicals in our food. So cool use case here again with that hyperspectral imagery. One of those bands is in the electromagnetic spectrum is the thermal IR band. And what we're measuring here is the emissivity is the term, but it's the amount of energy that's emitted in this infrared band. Through that processing step, we then can convert this emitted energy into temperature. And so basically this is, maybe some of us have been exposed to handheld FLIR cameras. During the pandemic, sometimes we had to get our temperature taken by a little gun before we went into public space. This is the technology that those systems are leveraging, is how much IR energy is being emitted from the surface of an area. So just quickly, three use cases here I've been a part of. In the upper right, bridge delamination. This is a process that my team developed. working with the Department of Transportation in Minnesota and Wisconsin. We've done some pilots here in Oregon as well. But we start to see the surface of the materials on a bridge deck can, what's called delaminate. They basically start to separate. This is a precursor to needing repairs on your bridge, asphalt failure. And this can be detected using IR imagery. Historically, this was a direct measurement process. So they'd have to shut the bridge down, stop the flow of traffic. They had some piece of equipment, I don't know what it was exactly, but they drag it behind a truck up and down the bridge. Took a couple days to do the assessment. With this technique, we were doing 1,000 bridges a day with an aircraft. And a camera like this didn't have to shut down traffic. We take a bunch of images, and if there are cars on the bridge deck, we'd use machine learning to take those cars out and layer a couple different thermal images together. So again, that value of remote sensing is instead of having to shut the bridge down and take direct measurements, we're able to do this remotely without interfering with the system that we're studying. Building heat loss, warehouses particularly are a good candidate for this, but by looking for thermal anomalies within the building, you're able to identify areas where you're having thermal loss. Basically, put some insulation in and improve your energy usage. Something that we've done with maybe a drone for just doing one large warehouse like this. We've had firms that they wanted to understand their candidacy pool across the city, and so we've done this with an airplane across the whole city and looked at every building in the city. Excuse me. And then last one there on the lower left, assessing the thermal conditions of our waterways. Very important for salmon habitat. Salmoid will only breed in, I'm not a salmon biologist, I'm not a fish biologist, so don't fact check me too hard, but I believe it's kind of a range of temperatures that are appropriate habitat for salmoids baby salmon to develop in. Particularly now that we're seeing a fair bit of dam removal start to gain traction here in the Pacific Northwest. As these waterways have water flowing through them again, wanting to understand that the natural course of those rivers supported some of these. It's part of the undamming of our rivers is understanding that the habitats we're creating are actually suitable for the species that we're trying to support through these activities. I've even worked with some nonprofits that they would revegetate the sides of banks to try to create shadier spots. Too much heat tends to be the larger issue with not supporting salmon habitat. Next technology I'll talk about, just time check, see what I'm doing. Next technology I'll talk about is LiDAR. LiDAR is an active sensor system and stands for light detection and ranging. Well, actually, I'll just pause real quick. This image that we're looking at, Dan Coe is someone in the geospatial industry I'm a big fan of. He just does these really beautiful visualizations using some of these data. And this is a river, there's the Willamette River, and it is colored by height. So the bright whites are deeper areas. The dark purples are higher elevation. And so what you can see in an image like this is that strong white line is where the river is today. All these other curves and lighter colors that we see are the paleo channels, where that river has been over time. So very cool, again, when we think about dam removal and restoring riverways that haven't had water in them for a long time, images like this help us understand what that river has looked like over time and what might be appropriate to try to support the reflow of that riverway. Well, LiDAR is a light detection and ranging is what it stands for, it's an acronym. It is the same as radar or sonar, but with a laser. And so your system is shooting a laser pulse. That laser pulse is hitting something on Earth and traveling back to the sensor. Because we know the speed of light, constant, at least in the vacuum, as we know how long, the system measures how long it took for that laser pulse to travel and strike an object and come back, we can understand the distance with very high level of accuracy and precision. Again, from an aircraft, 8, 10 centimeters, you get down to 3 centimeters, If you're doing this from a vehicle, 1 centimeter accuracy. So very detailed, very accurate mapping potential. One of the really valuable parts about LiDAR is that you get what's called multiple returns. And so that laser pulse, imagine it's maybe the size of a dinner plate, depending on how high you're flying or what kind of laser you're shooting, but size of a dinner plate. And that laser may come down and part of that energy may hit the top of the tree and go back. The rest of that laser may hit a branch in the middle of the tree and go back. And some of that energy is going to make it all the way down to the ground and return. So we now have data about not just structural data about what is above the earth, but this ability to see what is below the vegetation and map the ground, and I'll show some images or some examples of that. But one of the most powerful aspects of this technology. And then just a quick fundamental, the data created are called a point cloud. So each of these are measured dots. Each of these dots have struck something and come back, and they're all accurate within a couple centimeters. And we talk about the quality of a LiDAR data set in terms of, the term we use is pulses per meter, points per meter. And just think of if this room was 1 square meter and we had one measurement to understand or describe this room, well, if that measurement hit me on stage, we might think this room is 12 feet tall. If that measurement happened to hit there on the floor, we would think this room was 2 feet tall. So not as much detail as if we had 25 or 50 or 100 measurements to describe what was happening in this room. So the number of measurements in 1 square meter is how we describe the quality of a LiDAR point cloud or LiDAR data set. In the upper right, I believe this is around an 8-pulse data set, so 8 measurements per meter. And I think this is from the coast here. And what you can see is where there's nothing in the way in the lower right, that beach, man, look at what a nice smooth surface we have, all this nice data. We get a very clear understanding of what that beach looks like. In the upper left, you see some of those returns hitting the top of the bushes, and then in the red is that the red returns are the ground. So some of that laser energy is making it all the way to the ground. We can start to understand what the ground looks like beneath the vegetation. But in the middle, we've got some gaps. And I'm guessing some blackberry or some very thick vegetation that laser could not make it through, couldn't penetrate that vegetation. And so in this case, we have gaps. We don't know what's happening we can't describe the ground beneath that vegetation. That's an 8-pulse data set. Higher density LiDAR down here in the lower right, that I'm guessing 30 to 50 pulses per square meter or so, and you start to get an understanding. You can see the canopy structure of this forest. You can start to see, sort of understand the mid-story. You see some vegetation near the forest floor and very good representation of the ground as well. All the way to, I'd call this ultra-high density. That's probably from a tripod, honestly. But that's hundreds of pulses per meter. There you can measure just about any branch in that forest with that type of data. So again, you're really just trying to thread the needle between inexpensive, fast data to collect, very expensive, that's from a tripod, not really practical to collect a whole forest with that quality of data, maybe something in the middle here. But you're really trying to thread that needle between cost and how much information you need to answer the question that you're trying to answer. So if you want to understand forest structure, if I'm a forester and I want to know how many board feet per hectare there is, I can tell you actually can do that from 8 pulse per meter data. If I'm in the state of California and I want to understand a high level of detail of carbon sequestration potential of the forest for a cap and trade program, I need more like this to understand how much carbon sequestration potential there is in that forest. But these point clouds are very difficult to work with. You need very specialized software. So again, huge data sets. My laptop cannot deal with a point cloud like this in any meaningful way. And so we simplify those data into what's often referred to as a digital surface model or digital elevation model. So this is a digital elevation model of YAAS. It's a little blown out here, but we're very fortunate here in Oregon. The Oregon Department of Geology and Mineral Industries has collected LiDAR data from much of the state, including up and down the coast. This was a project that I was a part of early on when I started working in the field, and the Dogami's specification is 8 pulses per meter, so kind of what today we would describe as the lower end, although when they started this program 15 years ago, that was very cutting edge. Most people told us 8 pulse was crazy and we couldn't do it, but that's what we have here in Oregon. And you see the highest hit digital elevation image of YAAS. Well, sorry, let me step back, just describe. Digital elevation surface is basically taking all those returns from the point cloud and just taking a square, a pixel, and assigning it that value. So if that laser pulse hit this podium and this is 6 feet tall, I'm just gonna, instead of 8 different laser pulses, 8 pieces of data that my computer has to deal with, I'm gonna turn that into one pixel value. So really distilling the amount of information into something a little simpler and easier to digest. That highest hit digital elevation surface is just that. It's the first thing that LiDAR pulse hit. So it's the top of the tree, the top of the building, whatever it may be. And that's what we see on the left. In the middle, we've removed all the buildings, all the vegetation, and we have the bare earth model of YAAS. And YAAS Commons, a little tough to read, 22 feet tall, height of this building, at least that section of it, I think where we are right now, actually. And that's, pretty sure that's within 6 centimeters is the accuracy of that data set. This is online, and there's a link down there. You can Google Oregon LiDAR Viewer and get at this, and it's just web-based, so you can, excuse me, play around in here and download the LiDAR data if you want to work with it directly. So, bare earth model, brain starts churning. That ability to see below a forest or see below trees is very powerful. This is an area in Washington, again, because that gentleman Dan Coe who makes these great visualizations, he works up in Washington, so I'm going to use a few of those. But this is an area that, from a typical ortho image, typical photo of this area, heavily forested, very difficult to understand what's going on beneath that forest. With the LiDAR data, we can strip away those trees and see very clearly some failed terrain or landslides that have occurred. Worked on projects with the Oregon Department of Transportation to assess landslides or failed terrain as they were building roads. Excuse me. Fighting sore throat, so talking here, gonna take a couple breaks. But they've rerouted some planned roadways because we identified failed terrain in heavily forested areas. Very cool project I was able to be a part of. Mapped Mount St. Helens for several years. Sometimes you end up in Chemult, Oregon for a month at a time eating expired yogurt from the gas station for breakfast, and sometimes you get to hang out on Mount St. Helens for months at a time. Much more cool. But there's the growth of the cone, excuse me, regrowth of the cone over time that we mapped year over year, and so we're just combining these LiDAR data sets over time to look at change. Again, easy to do from an airplane, very difficult to do with direct measurements on the ground. Evident value, I will say that, so tsunami, delineating tsunami zones and understanding terrain at a high enough level of detail and accuracy to have a good sense of where water will flow under various inundation scenarios is something that LiDAR data is commonly used for. And so, again, as opposed to traditional survey techniques, which are taking direct measurements at certain locations and then kind of interpolating, guessing what it's like in between the measurements that were taken. With a LiDAR survey, we're able to do a much more complete assessment of the elevation profile of an area. And so, your tsunami maps have all been updated using that LiDAR data set that Dogami acquired. Excuse me. Infrastructure mapping. This is the Astoria Bridge. Very common application as well. If you're an engineer, you have a design file. You say, we should build a bridge like this. And your construction team tells you that it's crazy and you can never do it like that. The real world is messy. At the end of all the compromises that have to be made in the field, we want to compare the design file to what was actually created, to what was actually built, called the as-built assessment, to understand how close are we to the design. Do we meet the specifications that we hope to? And so, very common to use LiDAR data as part of construction projects to understand the final result and how that compares to the design file. And then change detection. We've done surveys of bridges like this, or buildings, other types of infrastructure, to understand if there's any movement, if this bridge is sinking or changing over time. Again, able to measure these things with centimeter scale accuracy. Excuse me. Electric utilities have been aggressive adopters of this technology, primarily for their vegetation management programs. Large source of wildfire here in the western United States is unfortunately trees that come in contact with power lines. We've seen that in Oregon. We've seen that in a very meaningful and sad way in California, which has a very real effect on communities down there. And so, again, these networks are tens of thousands or hundreds of thousands of miles of power lines. Trees are changing and growing all the time. Traditionally, these utilities had armies of utility foresters walking around in these areas, doing their best to understand, is this tree too close to this power line? Is that within our specification or not? The power lines that maybe are in front of our house, you might be able to do that relatively effectively. Many of these power lines traverse mountainous and forested terrain, where again, access is going to be very difficult, and they may be on the ridge, looking through binoculars, trying to understand if that tree is too close to the power line. So what many utilities do these days is fly helicopters and aircraft, collect LiDAR data over their power lines, and then we'll do an assessment to say, these are the trees that are too close to your power lines. We found that lots of risk was missed. They thought they had removed the risk from an area, and they had not. What we actually find more of is, because these entities are very risk adverse, is they're cutting down way more trees than they need to. And so through this process, we're adding precision, we're adding accuracy, and really helping them target their efforts where they need to be targeted. The other cool thing, again, adding these engineering designs into the equation. When I'm standing here, I can see where that power line is right now. Well, in the heat of summer, when everyone goes home and turns on their air conditioning and pumps a bunch more electricity through that power line, those things can sag 30 to 40 feet. High wind conditions, they can blow to the side 20, 30 feet. To visualize those scenarios when you're in the field, next to impossible. But with an analysis like this, we can drop in the engineering file, and the utility may choose to remedy an area for common case scenario or their high risk scenarios, depending on various parts of their decision-making process. We can also look at growth over time, to help planning and budget planning in the future, et cetera. So utilities have really, I don't necessarily think, have not traditionally thought of utilities as super forward-leaning, but in terms of adoption of some of these technologies, they've really been forward-leaning. Archaeology, I have a video, but for time, I think I'll skip it today. So again, that ability to remove the forest. This is Tikal, beautiful place. I've had the pleasure of visiting Tikal a couple times, really amazing. Ancient civilization, pre-Columbian civilization in Guatemala. And you see on the left what it looks like. It's a jungle. It's a jungle out there. And so that ability to, very difficult to traverse, to walk through that jungle, it's slow progress. And so that ability to, again, fly an aircraft over the area, remove the trees in the forest and see what lies beneath has really furthered the study of some of these areas. Tikal was discovered by British scientists in 1880 or something like that. And from 1880 until 2018, the extent of Tikal was described as that red square and kind of the dense white box here. Around 400 structures they had discovered since basically 120 years. So they did a LiDAR survey in 2018, and they found 60,000 additional structures. They used to think 1 million, 2 million people live there. Now estimates are maybe closer to 20 million. So there's another anecdote. I can't remember where this couple live, but they're an academic husband and wife team. They've been studying, I can't remember where they study, but they'd committed their life to a site similar to Tikal, and they'd been studying it for 40 years, and they did a LiDAR survey, and they seemed like good sports about it. They said, we learned more in 2 hours than we had learned in our 40 years of being on the ground here. So the ability to identify, again, artifacts that are below the forest, really powerful part of LiDAR. Real quick, just one last kind of emerging technology, synthetic aperture radar, space-based for the most part, heavily adopted in Europe and Japan. I don't know why we don't really use it here in the United States very much. We don't have the same level of expertise, but synthetic aperture radar works through a process called interferometry, and that sine wave, the radar wave, hitting the Earth, you're basically measuring where on that wave you're intersecting the Earth. And so this technology, within a single radar wave, this technology measures millimeter scale movements. So again, this is what we can use from space to understand terrain movement on geological time scale, fault line shifts or subsidence of tectonic plates. Interesting use case here on the right. This was a financial institution paid for this analysis. This is not something I was a part of, but I just know that this exists. I thought it was cool. These oil wells in China, again, tough to access. Oil storage wells are located in China, and they have a floating lid. Lid floats on top of the oil. And so they were using synthetic aperture radar to assess how much oil, crude oil, is in these storage vats to help them understand global fuel supply or global oil supplies and make their market bets appropriately. So again, just almost infinite applications of these technologies. And I think my best customers over time have been the ones that have said, here's the problem we're trying to solve. How could we go about doing it? And we look at all the sensors that we have access to, all the platforms that we can put them on, and just try to mix and match appropriately to see if there's a way to identify or solve those problems. So, with that, I think it's the end of my lecture, and we'll open it up to any questions. Thank you. Yeah.
So you mentioned drones and putting drones together with LiDAR. How small a scale and how reasonably can the costs, do you foresee the costs becoming? Are you going to be able to go to Costco, buy a drone, have it equipped with LiDAR, and tie into your gaming computer in the next 5 years?
I wouldn't be surprised. I do think some of that, like, there's an opportunity for kind of citizen science. There's an opportunity for kind of citizen data collection. If you have the newest iPhone, there's LiDAR on the newest iPhone. So that's the size and scale that we're talking about. An iPhone costs $1,500. I don't think it's survey grade LiDAR per se, but yeah, I mean, drone, a few $100 at this point. And LiDAR system, well, I don't know, I'm not usually shopping at the conventions, I guess, but you can probably get one for $1,500 or so. So yeah, pretty easy. I do think there is a dealing with the point cloud and that process of making it geographically accurate does require a level of expertise. And I have seen a lot of customers get burned because they thought it would be easy. You make the investment and sometimes it's the dollars that you pay, sometimes it's 6 months later you still are not sure if you've done it right. So that might be the challenge as much as anything. The hardware is less of an issue, I think, than the expertise, but again, with machine learning and some of the more software providers going cloud-based, access to that expertise is also increasing as well. So yeah, I think that sort of ability to do that stuff easily is definitely coming, and I don't think 5 years is too aggressive a timeline either.
Do you know the difference between LiDAR and ground penetrating radar and how they work together, and or whether or not, without getting conspiracy theory or anything like that, governments use those in comparison to just LiDAR as far as mapping?
So LiDAR won't penetrate the ground.
Yeah.
It is going to bounce off something and go back. Ground penetrating radar does. It is a wave that will travel through particular mediums. I've used ground penetrating radar to map utilities for Army bases, actually, where they buried all their pipes 40 years ago and now have no idea where they are. And so we'll use ground penetrating radar. It's a big lawnmower looking thing that you just push back and forth over the ground and look for what may lie beneath. The data are not well resolved. It is like less than a fish finder. You kind of you can see a thing. And if you're going back and forth, you see it linearly, you can maybe start to assume it's a pipe. But if you just saw like a dense rock that this might give you a return off of, you wouldn't be able to tell what it was. And I don't know that it's very easy to even tell like what the material was. It's almost assessing relative density of materials beneath the ground. So it's not a very high resolution. So you can do these combined maps where you might use LiDAR from above and then fill it in with ground penetrating radar from below. But you're never gonna, the beautiful, like here's what the tree looks like, you're never gonna see that from ground penetrating radar.
Like for instance, seeing root systems, you cannot, is there a machine out there that provides the LiDAR plus ground penetrating radar from above, or does it have to be two separate studies?
I think in two separate studies. I think for ground penetrating radar, you need to basically be in contact with the ground.
Okay.
Yeah. I saw one in the back of the house.
One of your pictures showed where landslides have been in Washington. You do the LiDAR picture.
Yeah.
And it looked like it showed the flow of where ground had moved.
Yep.
If somebody wanted to buy a lot, say in YAAS under the base of a hill, and wanted to know if there was landslide chance, would LiDAR tell them, or is there a map already existing that might tell you you're in a bad spot?
It would, and it does already exist. Now the data are from 2010, 2011. So that was the last assessment of this area that I know of. But
For that purpose?
For that purpose, if you go to the Oregon LiDAR, Oregon LiDAR viewer, there are several kind of check boxes on the side, and one of them is landslide presence. And the Department of Geology and Mineral Services has already delineated the landslides in this area using that LiDAR data. Now again, it's from 2010, so anything that's occurred since then won't be in that map, but yeah.
What was that website again?
Oregon LiDAR viewer.
Thank you.
Yeah, yeah.
I was just going to ask about bathyscaping. What are the technologies still sonar based and then spotmatic?
Yeah, good question. I almost threw one more slide in here for topobathymetric assessments. Deep water is sonar based. So if we're looking at, like on the East Coast, there's a lot of wind farm development now, and we're using sonar to assess the deep sea floor, look for unexploded ordnances, things like that. The middle shore, I'll say shallow waters, we use LiDAR. We use a green laser So most LiDAR is terrestrial LiDAR, where we're looking at the ground, uses a near-infrared laser, and it's going to hit the ground and come back. It's absorbed by water. So if you shoot a red laser in the water, it's gone. We use green laser to look in shallow waters, and that green laser will penetrate the water, hit the bottom of the river or lake or whatever, and come back up. It's only good for about 2 Secchi depths. Anyone know what a Secchi depth is? A Secchi disk. A Secchi depth is a measure of turbidity. A Secchi disk it's literally a disk. It's black, white, black, white. And you lower that into the water, and when you can't see it anymore, that's 1 Secchi depth. So if it's very clear water, like in the Caribbean, a Secchi depth might be 20 feet. So a green laser can penetrate maybe 40 feet in the Caribbean. In the muddy YAAS River after a rainstorm, you might only be able to see 6-8 inches. So it really matters how turbid your water is. But we do, and your question is very pertinent. I almost talked about it as part of that tsunami modeling. It's important to know once the water hits shore how it's going to behave. We can do that from the above ground, from the terrestrial LiDAR. But understanding how this wave is going to interact with the offshore environment requires mapping of that offshore environment. And near shore, if it's on shallow enough, we can use a green laser. As we get deeper than that green laser, we transition to sonar. And if we're doing deep shore, big surveys, we use big boats. People stay on the boats for weeks at a time. Now there's a lot of autonomous vehicles. They look like kind of a missile, and it's a submarine with these sensors attached, and you can tow them behind the boat. You can have them, just kind of remote control up and down the boat. And then it's that middle shore period that's tough, where the surf is crashing. And there's all, you see people on like ski-doos, like all sorts of kind of innovative ways to try to map that rough terrain near shore environment. That's the challenging one.
I want to talk about restrictions on the use of LiDAR and the data. And you mentioned Tikal, and I'm thinking more Mesa Berdie, Chaco culture area.
Mm-hmm.
It would seem to me that if the data is readily available, and if you have a huge area that you really can't police, I'm thinking about pot hunters, grave robbers, etc.
Yeah.
Is that data restricted in any way, or is it all publicly accessible?
It just depends on ownership of who commissioned the survey. So all the Dogami stuff is publicly available because that is paid for with, it's a combination of sometimes your tax dollars, but they bring in other nonprofits and they kind of bring these consortium members together to pay for the flight over, get some efficiency of scale. Utilities, like they own it. No one else can use it because there's liability issues. If they found a tree that was too close that they didn't mitigate, they don't want that out in the public. So it's typically is the commercial terms of the contract of where data ownership lies. But like there is a nationwide LiDAR data set commissioned by the USGS. It's only like 2 pulse per meter. So it's not very high detail. It was started 10 years ago or whatever. But that's all publicly available. But you're right. There is like, if you knew, there's some training to interpret the data, even that bare earth DEM, which is probably what you would use to look for structures or something like that. I've worked with groups that they had to do surveys for native archaeological sites prior to beginning construction, and they use LiDAR data for that. But it takes a fair bit to understand the difference between that is likely a site versus that's just a hill or a mound. But yeah, you're right. It tends to just come down to the commercial terms of the contract of where data ownership lies. That T-call stuff, though, it's some of both, right? There's a video. There's a National Geographic has a series that you can check out. Lynn is the explorer's name. I forget his first name, but in Tikal, they are on the ground and they do a LiDAR survey and they find a new temple. And I mentioned that British explorers discovered Tikal in 1840. plenty of people knew about Tikal way before that, and so everything, for the most part, it was very looted. This LiDAR survey, they found an undiscovered temple. It had been difficult to find, and that they found beautiful artifacts that were still there and that were still present in there. So it can go both ways, but you're absolutely right. Some of the data there, you can find sensitive things, and so it often is restricted.
Thank you so much.
How long does an average project take?
Oh, it really depends. A small area, you can turn around in a few days. If you're getting a drone crew out there, you can acquire the data in a day and process it in 2 or 3 days and deliver it kind of thing in a week. A large area, if we're mapping 20,000 line miles of power lines, might take 6 to 9 months. If you're doing the state of Oregon for the USGS, that can take several years. So it just depends on scale and the density of the data, how much compute. There's a lot of our processes that we might set up a compute process and hit go even with a large distributed compute network on premises or with the Amazon cloud. You might hit go and come back 2 days later and it's finally done with the compute. So yeah, it just depends. Cool. Well, thanks everyone for having me. Great organization, appreciate that.